for the columns, this remains the same, and this is the longitudinal bar, this is the ties, this is the longitudinal bar, and these are the ties. The next is the design of the beams, and there is also limitation on the ACE minimum, which is the minimum reinforcement that you must provide in the beams, and it is defined in section 9.6.1.2, and this is the section that these two equations, the governings, the maximum value should be taken to provide the minimum reinforcement. So in our case, BW is 18, D is 21.75, D is calculated like this. H is 24 inches, FC prime is 4000, and Fy is 60,000. And when you insert these values in equation A, it gives the value of 1.24 inch square, and you insert the value in the equation B, if it gives you 1.3. So this is the maximum. So this is governing equation B, that if there is no demand or the demand is less than 1.3, you must provide 1.3 inch square reinforcement in your beams. Let me calculate this on the spot. For example, I am calculating the equation B. This is the 200 into 18 is BW, and the 21.75 is the D, and let us divide it with the 60,000. You can see that the reinforcement that you must provide is 1.3 inch square, which is written in here. The next one is to check the ETABS results for your beams. But I have got the maximum value, because you will check the different beams of the same length for different stories, and I have taken the values for the top is 1.78 inch square, and for the bottom I have taken the value as 1.07 inch square. Let's go to the ETAB, and we will check on the beams. We'll click the longitudinal reinforcement. Now we'll check. So this is the beam. You can see the different values. The top value is the top reinforcement for the beam at the support. This is at the mid, this is at the support, and the bottom is the bottom reinforcement for the beams. This is at the mid span, this is at near the support, and this is the near the support. If you right click on it, again the same table appear, and you will go to the summary. These are the same parameters which I have explained, and we will check the design moment and flexure reinforcement, and you can see check the required rebars. For the top is 1.4, and for the bottom it is 0.9, and for the torsion there is no reinforcement required, because this is the capacity, threshold capacity of the beam in torsion. This is the 8.7 is the capacity, and 0.06 kip feet is the demand. So that's why the reinforcement is 0. So now we will check the maximum value of reinforcement in the top and the bottom. You can see it is 1.44, 1.63. This is 1.73 which I have taken. I will go up in the story 6. It is 1.65, 1.33, 1.3, 1.44, and just like that you have to check. You have to check the maximum value. It is 1.7, 1.67, 1.5, 1.02, 1.48, 1.29. And for example, this much reinforcement must be continuous in your beam, which is 0.35, and I have taken the maximum value of 0.7 for the continuous reinforcement, right? So the top we are getting the maximum value of 1.78 inch square, right? And for the bottom we will check again the bottom values. We will go up and now we'll move downward and we will see the maximum is 1.08 at the mid. This is 1, 0.78, 0.81, 0.99, 0.98. This is 0.97, 0.5, 0.8, 0.77, 0.98. So there is no value greater than 1.07. So let us calculate the number of bars. And the continuous reinforcement at the edges is 0.87. It means, for example, if you are using number 6 bar, it means you have to use continuous bars, 4 continuous bars, is because the 4 continuous bar area is 0.88. So for the bottom, we will divide just for the, as per the requirement is 1.07 divided by 0.44. So it says that you must provide 3 bars at the bottom, but we will provide 6 bars at the bottom with 4 bars continuous, because we need 4 bars to be continuous, as this value must be satisfied. 0.7, this is 0.88. If you multiply 0.44 with 4, it will give you 0.88, with which the E-tab says that you must provide continuous reinforcement this much, and this is 0.95. It means that it is not fulfilling the requirement that you must provide 5 bars, because this value is greater than 0.88. For example, if I provide 4, number 6 bar is continuous, so actually the area is 2 bars. The area is 0.88, so clearing 2 bars continuous is not enough to fulfill the requirement, right? Because this value is greater than 0.88, so you must provide more bars to be continuous. So if you make it 3 or 4, for example, make it 4, it is 1.76, and it is greater than the required reinforcement to be continuous in the bottom. So we will use 6 number 6 bars, in which 4 will be continuous and 2 will be there will be containment of the 2 bars. For the bottom, we will use 6 number 6 bars because it is 1.76 divided by 0.44. So you will need 4 bars at the support, near the column, but we will provide 2 additional bars and we will make it as 6. 2 bars will be continuous throughout the beam at the top, and 4 bars will be contained, because there will be containment of the bars as L by 3 and L by 4. The next is the design for the shear in the beams, and there is a requirement in the table 9.6.3.3 that for the non-pre-stress, creator of this equation and this equation should be adopted when there is no demand on the beams in the software. So using the equation A, if we insert the values, this is the FC prime, this is the width, this is the Fy, the value comes out to 0.14 inch square per inch, and for the equation from the equation B, it is 0.015 inch square per inch. And this equation governs that you must provide this much shear reinforcement in your beam when there is no demand. Let us go to the ETABS results. Again, we will check on the design output, click on the shear reinforcement, click on apply. You can see three values. Again, it shows the shear to be provided at the mid, at the this left support, at the near the right support. So it is 0.47 and the units are, you can check, you can go to the summary. The units are in inch square per foot. You can convert it into the inches or you can leave it as it is, right? So it is 0.1344 inch square and the maximum value which is 0.51 at the near the support, and at the mid it is 0.4. I have taken the value of 0.15 inch square per foot. This is actually not the values. These are the values. So this is the governing value and this is for the tabs. It is 0.4 inch square per foot and it is in the mid it is 0.3. This is just for the one type of the beam, and the next beam is B2, in which the demand is very high because we cannot apply this to this or this to this. We will make it two beams. The longitudinal reinforcement will be the same, but there will be difference in the shear reinforcement. So for the one beam it is 0.4 and 0.3. I have taken it as 0.4 for these beams in the vertical directions. This is 0.15. Somewhere else there is a value which is 0.4. This one 0.4 and 0.3, 0.4, 0.42. Because 0.46 is greater than 0.4, so we will keep that in the other type of the beam, which is 0.5. I think this is the beam, the short one. We can check these beams in which the value is 0.53, at the mid is 0.4, and this is also the same beam. This will be the same beam. You will be naming it in the during the drafting. You will identify and you will tell the draftman that these beams are different. Similar these beams. So there are two types of beams in which, in the first one, you can check it out in the model as well. I will upload the model. In the first beam, at the support it is 0.4 square per foot, and at the mid you must provide 0.3. So if you use two legs of number 3 bar, so you will need number 3 at the rate 6 inch near the support, and two legs of number 3 bar at the rate 8 inches at the mid. Similarly for the beam 2, near the support it is 0.55 and at the mid it is 0.44 inch square per foot. So you must provide two legs of number 3 bar at the rate 4.5 inches near the support, and two legs of number 3 bar at the rate 6 inches at mid. Right, so how do we do the calculation? Let me calculate the one just for your understanding, that you must write the leg. For example, the area of one leg of number 3 is 0.11, and if you using two legs it will becomes 0.22. So you must divide this area of the legs divided by the demand, and then you multiply this with 12 in order to convert it into inches. So it is 6.6 inches, so we are providing at the rate 6 inches centimeters. Similarly, the other calculation you can do that using the same concept. There's also a check on the maximum shear reinforcement on the beams, and it is the equation, the table 9.6.7.6.2.2 maximum spacing for the shear reinforcement, and it is same for the columns and beams. And I have told you we will check that for the beams, and it is similar for the columns, that this Vs will always be less than this values. That's why these two equations will be applicable. And we go to the 5, and let us check the member forces shear for the combo 2. You can check the value is 31. If I right click on this, the maximum shear value is 31 kip. In this beam, it is 28. This is 20. This is 30, 31. Right. So the value Vs we are getting is 31 kip. Let us calculate the capacity for 4 into square root of FC prime, which is 4000, into 18, which is BD, and into D, which is 21.75. This is in pound. You must divide it with the 1000. So the value, this value, 4 under root FC prime BWD is 99 kip, and Vs value we are getting from the E type is 31, which is, this value is greater than Vs. So this equation, these two D by 2 and 24 should be applicable. So if this value, for example, if the Vs is, for example, 120, so then the value 120 is greater than 19, then you have to check for against D by 4 and 12. So this was the whole story about the design of the columns and beams. So if you have any question, you can ask.